All right. On the first page, we said that given the given sigma square and n, right, the sample size, we don't know the sampling distribution of s squared. However, we do know the sampling distribution of this term here, right? N minus 1 times s squared divided by sigma squared. Right, so if you have sigma squared and n, you can find the sampling distribution of this. Well, when we say we know, it really means is we have a nice well-defined function to describe the shape. Okay, all right. So here's the key assumption, the key fact that we need first. Right? If the simple random sample of size n is selected from a normal population, this is a strong assumption, right? Because we have no way to know really if the sample really is from a normal population. But in order for this to work, this is the assumption that we have to assume. Right? Okay, so if this is true, then the sampling distribution of this funky looking term here is a chi-square distribution with an n minus 1 degree of freedom. Right? A chi-square distribution, so this is something new. We never seen this before yet in this class, but a chi-square distribution just have this kind of shape. Right? So think of it as a t distribution, right? Because it depends on this degree of freedom, and as the degree of freedom increases, right, this curve gets dragged out, and it look more and more like a normal distribution. And now, one unique thing about a chi-square distribution, and keep in mind, it starts at 0. So a chi-square distribution is only positive. It starts at 0 and it goes this way to infinity. Okay, and here is how this is distributed. Okay, all right. Now, so in that case, then we can take a look, right, at our problem that we stated in the first page. Right? Yeah. Suppose the population variance of income for California is 144. Let's write that down. And then we collected a sample of 51 people, n equals 51, and then we found the sample variance to be 185. Okay, what is the probability of our observation? Right? Right? Now we assume the population is normal. So check. We can apply that. Now what the question is asking, what is the probability that s squared is greater than or equal to 185, right? Given sigma squared equals 144 and n equals 51. Oh, by the way, why do I say greater than or equal to and not just equal to? Well, because it is continuous. And remember, in a continuous distribution, if I set any variable equal to a particular number, it's going to equal 0. Right? The probability will equal 0. So that's what we're trying to answer. But instead, we can't answer this. And so then we can answer this. We can kind of answer this question in a roundabout way. We can say, well, I don't know what the answer to that question is. However, I do know that n minus 1 s squared over sigma squared is distributed with a chi-square distribution. And so if right, and so that if I can find out what this is, then I can I can find the area, and that will be my probability. So let's first right, to get that, let's calculate this. Right, we call that chi-square equals, again, n minus 1 s squared over sigma squared. So n minus 1, that's 51 minus 1 s squared times 185 divided by 144. Okay, and we set that equal, and that is going to equal 64.236. Okay, so that means I have 64.236. Okay, and I know this term is a chi-square distribution, so therefore I can use either a table on the back of the book, or I can use an app, and I can find the area there. And what does this area represent? This area represents the probability that chi-square is greater than or equal to 64.236. Okay, and so equal. Okay, so we'll go to now we'll go to the app. Okay, so first thing though, we need the degree of freedom. Now so as I say in the first page, the degree of freedom is n minus 1, so which equals 50. Okay, now on your app here, you go to the chi-square distribution right there, and then you put in the degree of freedom, 50. And then I'm going to put in my x value, which is 64.236. 0.236. Okay, and then I want probability x is greater than the x here, and so I want the right tail. That's good, and there we go. That shows me that is 0.0849, right? Or 8495. Okay, and so that's that. So that is that probability. So how does this help us? Because remember, think about in the beginning, right? My goal is I want to know the sampling distribution of the sample variance. Now this is answering that question in an indirect way. But however, if you look at this formula here, right? Sigma square is fixed because that is the true population parameter, right? So given the sample size, right? Given the sample size, if I observe a larger, right? So the larger the s squared that I observe, right? The further away, right? This will be. So and it will be very unlikely. So this tells you the likelihood. This does indeed tell you the likelihood of you observing an s squared, but it's just scaled. It's just scaled with the population parameter, sigma squared. Right? So in a way, we can think of this as a kind of a standard normal, right? And we do not have to convert this to a standard normal anymore, right? Because we are dividing by the sigma square already. Okay.